Every object you observe in the night sky, including the sun and its planets, has its origins in an immense cloud of gas and dust. This audio course will guide you through the birth of our solar system, charting its journey from the gravitational collapse of a nebula to the emergence of complete worlds. This is an authentic saga of gravity, immense heat, and millions of years of development, the evidence of which is still imprinted throughout the cosmos. Our solar system, which serves as our shared home in the vastness of space, comprises a whole family of celestial objects, including the sun, planets, asteroids, and comets. But what can its creation teach us about the fundamental cosmic mechanisms that forge new stars and their accompanying planetary systems? By exploring how our own solar system came to be, you can not only grasp our own place in the universe, but also begin to decode the secrets behind the formation of other worlds. Our solar system's story starts within a dark and enigmatic cosmic nursery known as a nebula. You can picture a nebula as an expansive interstellar cloud of gas and dust, a realm where stars are both born and eventually perish. These colossal clouds serve a critical function as the universe's workshops, providing the raw materials and environment needed to construct entirely new star systems. The profound beauty of a nebula is that within its seemingly chaotic swirls lies the organized potential for new suns and planets. The history of our solar system's creation is rich with compelling theories and remarkable scientific breakthroughs. The solar nebula hypothesis, which was first conceived in the 19th century, posits that our star and all the planets that circle it were born from the gravitational collapse of one such gigantic nebula. The formulation of this groundbreaking idea, pioneered by key figures in astronomy like Pierre-Simon Laplace, takes us on an incredible journey through the evolution of scientific thought. An extraordinary sequence of events is set in motion when a nebula begins to contract under the force of its own gravity. This initial collapse is far from a simple singular event. It marks the start of a cosmic journey that will eventually transform clouds of gas and dust into fully fledged celestial bodies. Gravity, the same force you feel with every step, acts as the master architect of our solar system, drawing vast quantities of material together to build the dense, hot core that will ultimately ignite as the sun. As this gravitational collapse intensifies, the spinning nebula gradually flattens out into a vast, rotating structure called a protoplanetary disk, which becomes the primary stage for the drama of planetary creation. Can you envision yourself suspended within this swirling expanse of gas and dust, witnessing planets coalesce all around you? It is within this dynamic environment that new worlds are given the chance to form. At the very heart of this spinning disk, the relentless gathering of matter ignites the birth of our parent star, the sun. The sun's formation is a truly pivotal moment, akin to flicking a switch that illuminates an entire room. Indeed, life as you know it would be impossible without our star. The intricate process of transforming diffuse dust into a radiant star stands as a powerful testament to the fundamental wonders of our universe. The assembly of the planets represents an equally spellbinding chapter in our cosmic origin story. Through a process called accretion, material within the protoplanetary disk begins to clump together, giving rise to fledgling planets. Think of how tiny dust bunnies under a bed can gradually merge into larger masses. This is a cosmic-scale version of that process. It is a celestial ballet of gravitational attraction and accumulation, through which planets of varying sizes slowly take shape until they become the familiar worlds of today. You will notice that not all planets are created equal. The terrestrial worlds, like Earth and Mars, are primarily constructed from rock and metal, while the gas giants, such as Jupiter and Saturn, are fundamentally different, composed almost entirely of hydrogen and helium. This remarkable diversity in their makeup reveals much about the different conditions and creative forces at play across our solar system. The key factors driving these distinctions are each planet's distance from the Sun and the specific materials that were available in their region of the protoplanetary disk. Essential to this entire process are planetesimals, which are the small, foundational bodies that form within the disk. These celestial building blocks function like individual pieces of a grand cosmic puzzle, coming together to construct entire planets. Had they not formed, the evolution of our solar system would have followed a completely different path. The emergence of these crucial components is directly linked to the physical dynamics of the protoplanetary disk and the ever-present influence of gravity. Gravity is the ultimate force that binds our solar system, ensuring that planets maintain their stable orbits around the Sun. The profound impact of gravity is visible everywhere you look in our cosmic neighborhood, as it governed the formation and sculpted the final arrangement of all celestial objects. The organization of our solar system today is a direct result of these complex gravitational interactions that unfolded as planets and other bodies grew and evolved over eons. Another captivating process that shaped our solar system is known as planetary migration. Over the course of billions of years, the planets did not remain stationary, but instead shifted their positions, drifting through the protoplanetary disk in a vast, slow-motion cosmic realignment. This planetary movement had a profound influence on the ultimate formation and development of each world, and its consequences are clearly visible in the present-day layout of our cosmic home. The creation of moons and rings adds another layer of complexity to this epic tale. Have you ever considered how the moons that orbit planets actually come into existence? A great number of them are formed from leftover material in the disk surrounding their parent planet, while others are cosmic wanderers that were ensnared by a planet's powerful gravitational field. These smaller worlds, along with their beautiful ring systems, serve as enduring monuments to our solar system's long and dynamic history. Finally, any account of our system's origins must include comets and asteroids, which are the primitive remnants left over from its initial formation. Often referred to as cosmic fossils, these objects offer invaluable clues about the raw ingredients that constituted the original solar nebula. By studying their composition and origins, you can learn a great deal about how our own home in the universe was assembled. Consequently, comprehending our solar system's formation is not just about understanding our past. It is also about equipping ourselves with knowledge for the future. Every new discovery edges us closer to deciphering the great mysteries of the universe. The history of our solar system is a narrative of profound transformation, a story of how chaos gave way to order, with each star and planet finding its designated place in this immense and amazing creation. At the heart of this process are nebulae, the true stellar factories of the cosmos, where the lives of stars, and by extension planetary systems, have their genesis. But what exactly is a nebula, and what makes these cosmic structures so utterly captivating to you and me? A nebula is essentially an enormous cloud of gas and dust suspended in space, providing the precise conditions necessary for star birth. You can think of it as a vast cosmic workshop, a place where matter accumulates and starts to organize itself into something truly magnificent. While nebulae come in various forms, they all possess certain fundamental traits. Some, like the famous Orion Nebula, are luminous and brilliantly colored, while others appear as dark, opaque silhouettes that obscure the light from stars positioned behind them. So, how do these seemingly simple clouds of gas and dust evolve into something so spectacular? The role that nebulae play in the formation of star systems is of paramount importance. A nebula can remain in a state of equilibrium for millions of years, But if an external event, like the shock wave from a nearby exploding star, disrupts this delicate balance, the cloud will begin to collapse under the force of its own gravity. This collapse is the foundational step in the creation of new stars and, eventually, new worlds. As the nebula collapses, it fragments into regions of increasing density. While you might picture this as a chaotic free-for-all, it is in fact a remarkably orderly process. These dense pockets can achieve such extreme temperatures and pressures that hydrogen atoms begin to fuse together, igniting the birth of a brand new star. It is at this moment that the nebula transforms into a cradle of life, unleashing a flow of energy and radiating light out into the cosmos. The story, however, does not conclude with the star's birth. The residual material that wasn't incorporated into the star continues to spin and flatten, eventually forming a structure known as a protostellar disk. This swirling disk is the very location where planets will later be forged. Just picture a vast, spinning potter's wheel of cosmic material, and you'll understand why this disk is so critical for the formation of the celestial bodies that will become planets in orbit. Within this disk, microscopic particles of dust and gas start to collide and merge. This process of accretion gives rise to planetesimals, the small foundational bodies that serve as the building blocks for planets. Through countless collisions over immense timescales, these planetesimals accumulate more and more material, their growing mass and gravity allowing them to attract even larger quantities of gas and dust. Isn't it incredible to consider that entire worlds can be constructed from such humble beginnings? Nebulae also serve as cosmic reservoirs for a rich diversity of chemical elements. Inside their cores, stars forge heavier elements through the process of nuclear fusion. When these stars eventually reach the end of their lives, they expel these newly created elements back into space, enriching the surrounding nebula. This enriched material then becomes the raw ingredient for future generations of stars and planets, in a perpetual cycle of cosmic creation and destruction. Beyond their role as stellar nurseries, nebulae are indispensable for our broader understanding of the cosmos. By carefully studying these immense clouds, astronomers can piece together how our own solar system was formed, and even speculate about the conditions necessary for life to emerge elsewhere in the universe. You could say that every nebula is a story waiting to be told, a cosmic puzzle that links us to both the past and the future of our galaxy. Nebulae also fundamentally shape how you and I perceive the universe. Many of these structures are brilliant sources of multicolored light that we can observe from Earth, and their spectacular images offer more than just aesthetic pleasure. They provide us with a deeper insight into the very nature of the cosmos. When you gaze upon these celestial clouds, you are, in a sense, looking at fragments of our own origins, a powerful reminder that we all belong to the same vast cosmic home. So, what is the ultimate lesson nebulae can teach us? Looking past their sheer beauty and mystery, they reveal the profound interconnectedness of every component in the universe. Every star, planet, and moon that you know of began its existence inside a nebula, reminding us that we are all participants in a much larger cosmic cycle. Understanding nebulae allows us to better appreciate not only our solar system's formation, but also the real possibility of other solar systems existing in the infinite expanse of space. In the end, nebulae are far more than just passive clouds of gas and dust. They are dynamic crucibles where stars are ignited, where planets take shape, and where the many different stories of the universe are woven together. Grasping their central role in the formation of star systems helps us unlock the secrets of the cosmos and extends an open invitation for you to continue exploring all that we have yet to discover in this immense and mysterious universe. The solar nebula theory stands as one of the most compelling explanations for how our solar system came into being. Have you ever paused to wonder how our own home in the universe was constructed? To truly comprehend it, you need to be familiar with the history of the theory and the pioneering individuals who shaped it. It all begins with the simple concept of a nebula, a massive cloud of gas and dust, primarily hydrogen and helium, drifting through space. This idea that our solar system originated from a nebula is not a recent development. The German philosopher Immanuel Kant first put forward the concept back in the 18th century. It wasn't until the 19th century, however, that other brilliant minds, such as Pierre-Simon Laplace, began to investigate the theory more deeply. You can only imagine the intellectual thrill these scientists must have felt, trying to solve the puzzle of our cosmic origins as research into the idea grew progressively more complex over time. The prevailing hypothesis suggested that the nebula caved in on itself due to its own gravity, which in turn produced a revolving disk of material. But you might wonder how scientists arrived at this idea. They began by studying other stars in different phases of their life cycle, and found that many were encircled by comparable disks, a critical piece of evidence that helped to validate the theory. The gravitational collapse of a nebula isn't an abrupt event, but rather a gradual evolution that unfolds over millions of years. At first, the cloud of gas and dust is mostly uniform, but over time, minor inconsistencies emerge. These irregularities act as seeds for increasing density, allowing gravity to start pulling matter together. If you've ever watched a vortex take shape in water, you have a good idea of how small disturbances within a nebula can cause material to concentrate in specific zones. Eventually, this process transforms the vast cloud into a protostellar disk. You can picture it like a chef spinning pizza dough in the air. The material flattens and expands as it rotates. It is within this very disk that the astonishing process of planet formation begins, as the revolving matter also starts to coalesce into larger and larger celestial bodies. At the very heart of this protostellar disk, gravity's influence continues to intensify. The buildup of matter becomes so extreme that it ignites the birth of a star, our Sun. This event is truly remarkable, as the nuclear fusion deep within the Sun's core unleashes a colossal amount of light and heat, which ultimately provides the energy for life in our solar system. Did you know the Sun holds over 99% of the entire solar system's mass? As the Sun takes shape, the remaining material in the disk is far from inactive. Planets start to form through a process of accretion, where dust and gas particles collide and merge, building up into progressively larger objects. These bodies, which you know today as planets, are the outcome of a slow yet persistent construction project, almost like a game of cosmic building blocks, where tiny pieces combine to create something immense. The solar nebula theory does more than just explain the origins of the Sun and planets. It also invites you to investigate their diverse characteristics. For instance, have you ever questioned why our solar system hosts both rocky planets and gas giants? The explanation is found in their distance from the Sun, as the temperatures and pressures in various regions of the disk dictated the final composition of these worlds. The story behind the solar nebula theory stands as a tribute to human ingenuity. Through centuries of dedicated research and groundbreaking discoveries, we have achieved a much clearer understanding of our own position in the cosmos. As our technology progresses, the instruments we use to investigate space grow more sophisticated, allowing you to see further into the universe than ever before. The solar nebula theory is not merely a scientific explanation of our beginnings. It serves as a powerful reminder that the universe is teeming with mysteries, just waiting for you to uncover. The pursuit of knowledge never ends, and each answer we discover invariably leads to a host of new questions. So, the next time you find yourself looking up at the star-filled sky, remember that every star, planet, and comet has its own unique story. The solar nebula theory represents just a single chapter in this magnificent cosmic narrative, a story that continues to unfold as you explore the vast and amazing universe that envelops us. Every minor impact holds significance, as these tiny fragments steadily accumulate into larger bodies, which in turn exert a stronger pull on even more matter. Gravity is the central force in this entire sequence, not only drawing material inward like a magnet, but also choreographing the intricate movements of all objects within the disk. You can visualize it as a celestial dance floor where gravity sets the rhythm. If any single body moves too quickly, it risks a collision, throwing the entire system out of balance. This delicate equilibrium is precisely what allows planets to form. Of course, the process is far from perfect, and the protoplanetary disk is as much a battlefield as it is a nursery. Gravitational disruptions frequently knock objects from their stable paths, triggering chaotic interactions that can lead to spectacular collisions, the fragmentation of developing worlds, and even the birth of moons. In every instance, however, it is gravity that ultimately dictates the destiny of these celestial bodies, shaping the final outcome from the turmoil. The sheer amount of time this requires is astonishing. A new solar system's formation from a collapsing nebula doesn't occur in an instant. Rather, it's a process that can span millions of years, a timescale that feels almost beyond our comprehension. In the context of the universe, however, this is barely a whisper. As the nebula disperses and heat intensifies at the core, nuclear fusion finally ignites, giving life to a new star. Yet the work isn't finished, as gravity continues to sculpt the disk, gradually assembling the planets. So, when you gaze up at the stars in the night sky, you can recall that each one has its own profound history. Their journey begins with the gravitational collapse of a nebula, an event that ties everything together in this immense cosmic web. Gravity isn't merely a force of attraction, it is the grand architect of the universe, responsible for shaping the very worlds we inhabit. The next time you look at the stars, consider that initial moment, how gravity played its essential role, and how, after millions of years of transformation, we were given a home in this corner of the cosmos. At the very center of a collapsing nebula, a truly captivating phenomenon unfolds, the creation of the protoplanetary disk. To understand what this is, imagine how matter behaves as the nebula condenses. Because of a fundamental principle known as the conservation of angular momentum, the material inevitably begins to rotate. As it spins faster, the matter that was once widely dispersed flattens out into a vast, swirling plane, forming a disk around the object that will soon become a star. This protoplanetary disk is composed almost entirely of gas, dust, and ice, the raw materials found in abundance throughout the nebula. These components are absolutely vital. For over immense stretches of time, they will be transformed into the planets, moons, and all the other celestial bodies we recognize today. You can think of this disk as a colossal cosmic kitchen, where all the necessary ingredients are being blended together to create vastly different worlds. Inside this disk, the planet-building process starts with countless collisions between minuscule dust particles. This leads to a chain reaction where these particles stick together, resulting in the aggregation of larger objects known as planetesimals. These bodies are the initial building blocks of planets, representing an early and crucial stage of their development. As these planetesimals grow larger, their own gravity becomes a dominant force, allowing them to attract surrounding material much more efficiently and speed up their evolution into full-fledged planets. Not all of the material in the disk, however, is destined to become part of a planet. A significant amount of debris is left over, remaining in unstable orbits as the asteroids and comets we see today. Over time, the disk also begins to differentiate based on temperature. In the hot inner regions closer to the star, heavier solid materials form rocky planets like Mercury, Venus, and Earth. Meanwhile, in the colder outer zones, conditions allow ice and gas to accumulate, creating gas giants like Jupiter and Saturn. And how can we be certain this is how it happened? The clues are provided by observations of other still-forming star systems. Across our galaxy, astronomers have found protoplanetary disks at many different stages of evolution, and they show features that strongly mirror what we believe our own solar system's disk once looked like. The story doesn't end there either. As planets mature, their gravitational influence on one another can cause their orbits to shift, a process called planetary migration, which is key to understanding the final architecture of our solar system. While impacts between young planets and smaller celestial bodies can be incredibly violent and destabilizing, they also create opportunities for new worlds to emerge. Every one of these collisions has the potential to form moons, rings, or even entirely new planets, thereby adding rich layers of complexity and wonder to the history of our solar system. When you consider the formation of the protoplanetary disk, you realize it is essentially a cosmic ballet of matter and energy, where every rotation, impact, and interaction contributed to the birth of our home in the cosmos. So, the next time you gaze upon the night sky, I want you to remember that you are looking at the magnificent result of an immense and captivating process that started billions of years ago inside a nebula. The story of the protoplanetary disk is fundamentally a narrative of connection, transformation, and ultimately, creation. It all begins with a colossal sphere of gas and dust, superheated and beginning to stir with life, marking the moment our star, the Sun, commences its formation. To grasp this process, you must first picture the core of the protoplanetary disk, where all the matter is drawn together. Gravity, the same force that anchors us to Earth, plays the central role here. But how does this force manage to convert a swirling cloud of gas into a radiant star? Initially, the material at the disk's center acts like a giant magnet, as gathering dust and gas allows gravity to pull in even more material. This is much like pouring sand into a funnel. It falls chaotically at first, but as it collects, it compacts into a more solid mass, a fundamental step in the Sun's creation. As this material accumulates, the pressure at the center intensifies dramatically. You can think of it like squeezing an air-filled balloon. The more you compress it, the more the air inside pushes back and heats up. In the same way, the pressure at the heart of the protoplanetary disk becomes so extreme that it starts to generate immense heat. This thermal energy is absolutely essential for the next phase of the Sun's development. But what exactly follows? As the temperature climbs, something truly remarkable occurs. Hydrogen, the universe's most common element, becomes ionized. This means its electrons are stripped away from their nuclei, which forges a sea of charged particles and releases a tremendous amount of energy. At this stage, the forming sphere starts to emit a faint glow, much like a light bulb that heats up just before it fully illuminates a room. The Sun, in this embryonic phase, exists as a sphere of hot plasma. With the temperature continuing to soar, a critical threshold is eventually reached, igniting the process of nuclear fusion. So what is nuclear fusion, and why is it so significant? It is the reaction where hydrogen nuclei fuse together to create helium, unleashing a colossal burst of energy. This is the very instant the sun truly comes alive, beginning to radiate the brilliant light that we see today. However, this birth was not a sudden event. It unfolded over millions of years as the sun continued to gather material from the surrounding disk and expand in size. But what became of all the matter that wasn't absorbed into the sun? That leftover material in the disk started to coalesce into other bodies. Some particles clumped together to become planets, while others formed the asteroids and comets we know. The deciding factor in this cosmic sorting process is gravity. Larger masses attract more material, growing into giants, while smaller ones are often left behind in a gravitational game that determines their celestial destiny. Once the sun stabilized, it began to profoundly shape its environment, with its light and heat impacting the planets that were forming around it. This solar energy was the catalyst that heated the raw materials of the planets, allowing them to start solidifying and developing surfaces. This marks the point where Earth and its planetary neighbors began to truly take shape, each one developing distinct characteristics based on its composition, its history, and its distance from the central star. As the sun directs its light outward, Earth starts to receive a constant flow of energy. This energy stream is not just vital for life as we know it, but it also established the precise conditions that allowed for the development of an atmosphere, and eventually, life itself. The sun's gravity orchestrates the entire system, creating a cosmic dance where every planet traces its own unique orbit, yet all remain bound together by this invisible force. Can you imagine witnessing this spectacle from afar, watching planets form in a breathtaking display of light and motion? Over eons, the sun matured into a stable star, its light now acting as a beacon for the planets in its orbit. The chronicle of its formation reveals how a simple swirl of gas and dust can evolve into a source of life-giving energy. This act of creation was just the prologue to a story that would span billions of years and continues to shape our existence on Earth. The sun's formation isn't merely a fascinating astronomical event. It's an invitation for you to contemplate our own position in the cosmos. Have you ever considered what other secrets the universe might be holding? To find the answer, you must delve into the world of accretion, which is the foundational process behind the creation of our solar system. You have to picture the protoplanetary disk as a vast expanse brimming with material. Inside this disk, minuscule particles of dust and gas are constantly swirling and circling a huge developing star at its center. These particles inevitably collide with one another, and as they do, they begin to stick together, merging to form progressively larger structures. Through this relentless series of collisions, the dust particles coalesce into what we identify as planetesimals, which you can think of as the fundamental building blocks for planets. These celestial bodies, with sizes that can vary from that of a large mountain to a small moon, represent a critical step in the journey toward planetary formation. Their gradual accumulation sets the stage for everything that follows. So, how does a planetesimal evolve into a full-fledged planet? The key lies in the escalating power of gravity. As these planetesimals gather more mass, their gravitational pull intensifies, allowing them to attract even more dust, gas, and other planetesimals from their surroundings. This gravitational feedback loop creates a runaway effect, accelerating their growth and transforming them into protoplanets, the direct ancestors of the planets you recognize today. However, you should understand that the path to becoming a planet is anything but peaceful. Protoplanets frequently smash into each other in cataclysmic events. While these collisions can be incredibly destructive, they are also a primary mechanism for growth. When two of these massive bodies collide, they can merge to form an even larger object, a crucial step that allows planets to increase their size and complexity over millions of years. Not every protoplanet, however, is destined to become a behemoth like Jupiter. Planets such as Earth took shape in the warmer inner regions of the protoplanetary disk, where the available building materials were scarcer. This explains why terrestrial planets like our own possess a different scale and makeup than the gas giants. The diverse character of the planets in our solar system is a direct result of the specific local conditions under which each one was born. This naturally leads you to wonder why some planets have moons while others do not. The explanation is embedded within the very process of their creation. Moons can either form from a disk of leftover material that a protoplanet gathers around itself, or they can be rogue asteroids and other bodies that are captured by a planet's immense gravitational field. These gravitational interactions are what give our solar system its dynamic and richly varied architecture. As these emerging protoplanets continue their growth, they eventually begin to dominate their orbital paths. This means they either absorb or gravitationally eject any smaller objects that cross their trajectory, effectively clearing out their neighborhood. By establishing this orbital dominance, a planet can continue its development without interference from other bodies that might otherwise disrupt its formation. At the same time, you'll find that temperatures and pressures varied dramatically across the protoplanetary disk, which had a profound impact on what the planets were made of. Closer to the Sun, where the heat was extreme, only rock and metal could condense, leading to dense, terrestrial planets. Farther out, in the frigid depths of space, vast quantities of gas and ice were available, allowing colossal gas giants to form. Ultimately, the birth of planets is just one phase in a much grander cosmic story. As the solar system matured, intricate interactions between planets, asteroids, and comets continued to shape it. You can see the evidence in the colossal impacts that have scarred planetary surfaces, with each collision adding a new detail to the long history of our solar system. The allure of studying planet formation is that it reveals so much about the evolution of the cosmos itself. Every planet serves as a unique chapter in the vast narrative of the universe, and its distinct characteristics invite you to explore and better comprehend our own position within this infinite expanse. Earth itself, with its unique atmosphere and capacity for life, is merely one entry in a cosmic story that is still being written as the universe expands. This entire process encourages you to examine the profound differences that separate the terrestrial planets from the gas giants. So what truly distinguishes these two planetary types? To put it simply, you can contrast them as you would a solid ball of rock against a massive, swirling cloud. While both are planets, their composition and fundamental structure could not be more different. Just as you observe countless variations between land and sea on Earth, space presents these distinctions on an awe-inspiring scale. Let's begin by examining the terrestrial planets, which are the four worlds orbiting closest to the Sun: Mercury, Venus, Earth, and Mars. You can picture these as solid, compact bodies composed almost entirely of rock and metal, with firm surfaces that you could theoretically stand on. Their existence is the outcome of heavier materials clumping together through accretion, a process where gravity painstakingly pulled these dense elements together over eons. In stark contrast, we have the gas giants, Jupiter, Saturn, Uranus, and Neptune. You might then ask how it is possible for these planets to be so fundamentally different from their rocky siblings. Their formation story unfolds in the cold, outer reaches of the solar system, where a completely different set of ingredients and conditions prevailed. Have you ever found yourself wondering about the origins of planets? Within the immense cosmic dance of space, a central role is played by what we call planetesimals. You can think of them as the basic building blocks in the universe's grand construction yard. These small particles of rock and ice are the essential bricks that, through the persistent pull of gravity over vast stretches of time, assemble into the planets we recognize today. Planetesimals are solid objects that came into being during the earliest phases of our solar system's formation. As the primordial solar nebula started to collapse, these tiny bodies were formed from the clumping of dust and gas swirling within the protoplanetary disk. To help you visualize this, picture a fierce blizzard where individual snowflakes collide and stick together, gradually forming much larger snowballs which then continue to grow. So what makes these planetesimals so critical to the development of our solar system? The answer is found in their function as the architects of planets. As they group together and expand, their gravitational pull begins to attract more and more surrounding material. Imagine yourself as a magnet moving through a field of metal filings. As you travel, you continuously gather more and more iron particles. Planetesimals operate in a similar fashion, accumulating matter and steadily increasing their mass and size. Now, let's explore the transformation of these small bodies into full-fledged planets. As planetesimals enlarge, they start to assert gravitational dominance over their own orbits, becoming powerful enough to draw in other, smaller planetesimals nearby. This gradual accumulation is a process known as accretion, much like how a snowball gathers more snow and expands with every roll. Ultimately, a few of these growing bodies will achieve planetary status, while countless others will be left behind as asteroids or comets. It turns out, however, that not all planets created from this process are alike. The key difference between the rocky terrestrial worlds, like our own Earth, and the colossal gas giants, like Jupiter, can be traced back to their formation. The larger planetesimals, by gathering enough gas, swelled into immense gaseous spheres. This divergence in their makeup is largely explained by their distance from the central star in the primordial nebula, where warmer inner regions favored rocky materials, while the colder outer regions allowed for the accumulation of gas. The explanation for this planetary divide is rooted in where they formed within the solar system and the materials present there. While the rocky planets took shape in the hottest interior of the protoplanetary disk, a zone rich in metals and rock, the gas giants emerged much farther out in the frigid depths. In these colder regions, not only were rock and metal available, but so were immense quantities of gases like hydrogen and helium, allowing them to become the giants they are. This distinction in origin led to vastly different evolutionary paths. The terrestrial planets, being so near the sun, endured extreme temperatures and varied atmospheric pressures that sculpted their surfaces. Earth, for instance, possesses liquid water, which enabled life to arise, whereas Mars, though it might have had water in its past, devolved into a cold, desolate world. By contrast, the gas giants cultivated thick, complex atmospheres, complete with elaborate systems of rings and a multitude of orbiting moons. This raises a fascinating question. How do these profound differences impact the possibility of life? While terrestrial worlds seem to offer more hospitable conditions, the gas giants, with their violent storms and crushing pressures, appear far less welcoming. However, we shouldn't dismiss the potential of the moons orbiting these giants. Worlds like Europa or Enceladus may conceal vast liquid oceans beneath their frozen shells, presenting environments that could very well be suitable for life. Furthermore, a planet's composition directly influences its gravitational pull and, by extension, its capacity to capture and hold an atmosphere. Larger planets like Jupiter wield such immense gravity that they can sweep up enormous volumes of gas, resulting in atmospheres that are far denser and more expansive than those of any terrestrial world. This dynamic also means that gas giants serve as cosmic guardians, their gravity attracting stray materials and shielding the inner solar system from potential impacts. These fundamental differences also dictate the formation of moons. Rocky planets typically have very few moons, if any, and they tend to be quite small. On the other hand, the powerful gravity of Jupiter and Saturn has enabled them to capture a vast collection of moons, some of which are even larger than the terrestrial planets themselves. This phenomenon reminds us that all bodies in the solar system, no matter how different they appear, are interconnected in a grand cosmic ballet. As we delve deeper into this story, we realize that the history of planetary formation is also the narrative of our solar system's evolution. Across millions of years, these celestial bodies have undergone collisions, shifted their orbits, and altered their compositions. The intricacy of this entire process is like a complex puzzle, where every single piece is essential to forming the complete picture, from the initial planetesimal bombardments on early Earth to the system we see today. All of this inquiry ultimately leads us to a more profound question. What can our planetary neighbors teach us about the formation of other solar systems throughout the galaxy? The sheer diversity in the creation and characteristics of the planets here may hold the keys to understanding how planetary systems take shape in distant corners of the universe. The incredible variety we observe in our own cosmic backyard could be a reflection of the rich tapestry of worlds that we have yet to discover. An era of intense collisions, known as the Great Bombardment, was instrumental in sculpting our world, giving rise to its oceans and continents, and possibly contributing the very water we have today. Yet, not every one of these formative bodies was destined to become part of a planet. When a planetesimal failed to merge, it might instead embark on a solitary journey through space as a wandering asteroid or comet, providing us with invaluable information about the materials that constituted the early solar system. The story of these planetesimals extends far beyond the initial creation of planets, as they continue to play a crucial role while the solar system evolves. Gravitational interactions, for example, can alter a planet's orbit or redirect these smaller objects into comets that approach the Sun, allowing us to learn more about our solar system's past. The fact that some of these planetesimals have survived to the present day means we have direct access to these cosmic time capsules. Thanks to sophisticated space missions, we have been able to study asteroids and comets, which are the enduring remnants of that primordial epoch. These celestial bodies are not only captivating to observe, but they also hold vital clues regarding the composition of the solar system and the mechanisms by which planets formed. Planetesimals are truly the unsung heroes of our solar system's genesis. Though small compared to the worlds they helped fashion, their role was absolutely fundamental. By understanding their existence and evolution, we can grasp not only how planets were built, but also the unique history of our own home, Earth. So, the next time you find yourself looking at a star in the sky, I want you to remember that behind its distant glow lies an incredible story, one that originates with the simplest building blocks in the vast workshop of the cosmos. Gravity is the mysterious force that governs everything we know in the universe. But what part does this force play in shaping the celestial bodies within our own solar system? I'd like you to imagine being in a large hall filled with balls of various sizes. If you suddenly rolled a heavy bowling ball into the center, you would see the smaller balls get drawn toward it. In much the same way, gravity acts like that cosmic bowling ball, influencing the formation and organization of planets and other celestial bodies. When a nebula begins to collapse under the influence of gravity, it not only concentrates in one point, but also starts to rotate. To visualize this, think of a spinning top. As it spins, its shape flattens. The exact same thing occurs with nebulae. As the material in the nebula clumps together, it begins to rotate faster and flatten out, forming a disk. It is within this disk, a direct result of gravitational collapse, that the magic of planet creation is set to unfold. But what if gravity simply did not exist? The result would be absolute chaos. Stars would never form coherent systems, planets would not have defined orbits, and the universe would be an entirely disorderly place. Gravity is the very reason Earth orbits the Sun and why the Moon circles our planet. Without this essential force, everything we know about our cosmic neighborhood would be profoundly different. As a protoplanetary disk forms, gravity also plays a decisive role in the accumulation of matter, preventing planets from simply drifting away into space like marbles on a tilted surface. Tiny particles of dust and gas attract each other, creating a kind of domino effect that causes them to cluster into larger bodies we call planetesimals. I invite you to imagine being one of these small particles within a massive disk, drawn to other bodies as you all spin at immense speeds, in a fascinating process that leads to the formation of entire worlds. Gravity not only influences the formation of planets in the solar system, but also determines their individual characteristics. For example, a planet's gravity dictates its ability to retain an atmosphere. Larger planets, such as Jupiter, have powerful gravity, which allows them to hold on to light gases like hydrogen and helium. Meanwhile, smaller planets like Mercury possess weak gravity and are unable to retain a significant atmosphere, explaining why some worlds have skies filled with clouds, while others are barren deserts. The influence of gravity also extends to the formation of moons and rings around planets. You can picture a party where a large disco ball hangs at the center, surrounded by many people. If someone were to gently push a person toward that ball, the person would begin to orbit around it. The same thing happens with moons, which are drawn in by a planet's gravity. Sometimes this attraction is so strong that it forms entire rings of material orbiting the planet, like the magnificent rings of Saturn. In the grand context of our history, gravity is also responsible for an intriguing phenomenon known as planetary migration. Over millions of years, entire planets can move and change their orbits because of gravitational interactions with other bodies. You can think of it like a group of friends at a party deciding to switch places, with one moving toward the center while another moves away. In a similar manner, planets can shift their positions in space, often influenced by the gravity of nearby celestial objects. This constant gravitational interaction affects not only planets, but also the comets and asteroids that inhabit our solar system. These smaller bodies, formed from the same materials as planets, are constantly being pulled by the gravity of larger objects. This dynamic can lead to exciting situations, such as an asteroid being sent on a trajectory toward Earth, or a comet approaching the Sun and shining brilliantly in our night sky. It is truly fascinating to reflect on how this single fundamental force has shaped our home in the universe. Every time we gaze at the starry sky, we are observing the direct result of billions of years of gravitational influence. The arrangement of planets, the formation of moons, and the existence of rings are all products of this powerful force. It even provides us with a sense of stability in our everyday lives. Ultimately, without gravity, we would not be here to marvel at the vast cosmos. You couldn't take a step, leap into the air, or even draw a breath without gravity's influence. From the moment you rise from bed to when you settle into a chair, this fundamental force is constantly anchoring you, a silent partner in your every action. Gravity serves as a perpetual reminder that even within a seemingly chaotic cosmos, powerful forces exist to impose order and create structure. As our comprehension of the universe deepens, this force consistently remains at the heart of scientific exploration and discovery. Across disciplines, from the quantum realm to the vast scales of astrophysics, researchers are dedicated to unraveling how gravity governs the birth and development of star systems. This ongoing work raises profound questions about the secrets it has yet to reveal and how it will steer the destiny of our solar system and the worlds beyond it. Every new finding peels back another layer of gravity's complex character, acting as the common narrative thread in epic cosmic events, from a black hole consuming a star to a new world taking shape. So, when you next gaze up at the night sky, I want you to appreciate that each star, planet, and moon you see is a testament to this extraordinary force, the very power that has orchestrated the celestial ballet since the dawn of time. But what occurs when a planet shifts from its original cosmic position? This question leads us to planetary migration, an enthralling process that unveils some of the solar system's most profound secrets. You see, planets are not static celestial bodies. They are more akin to performers on an immense cosmic stage, constantly shifting and adjusting their positions over eons. To grasp what drives these celestial movements and which forces are responsible, let's revisit the analogy of a dance floor. Picture a group of dancers, each with a unique rhythm, starting in set places. As the music plays on, they begin to reposition themselves. In our cosmic scenario, that music is gravity, the immense force that dictates the orbital paths of the planets. During the solar system's infancy, the planets settled into a variety of initial orbits. But as the protoplanetary disk of gas and dust began to cool, these worlds started to gravitationally influence one another, like subtle nudges on the dance floor that could shift a planet's path closer to or farther from the sun. This naturally leads to a compelling question. How can we determine when and where these planetary relocations happened? To piece together this history, scientists have meticulously analyzed the present-day orbits of the planets. They concluded that the orbits of gas giants like Jupiter and Saturn are unlikely to be the same ones they originally occupied. The prevailing theory posits that because these planets are so immense, their gravitational fields rearranged surrounding material, creating a gravitational wind that dragged them into new orbital paths, much like a large magnet pulling smaller metallic pieces along with it. And this phenomenon isn't limited to the gas giants. Evidence suggests that rocky planets, including our own Earth and Mars, may have also shifted during their formative years, like smaller dancers guided by unseen partners. This brings us to the most thrilling implication: migration's impact on a world's potential for life. A planet that drifts too close to its star risks overheating and losing its atmosphere, while one that moves too far out could become a frozen wasteland. These shifts are far more than mere movements. They can be the deciding factor in a planet's ability to host life. For instance, researchers propose that Jupiter's own migration likely had a profound effect on the asteroid belt. As Jupiter traveled through the early solar system, its immense gravity could have stirred up the material in this region, preventing it from ever coalescing into a new planet. To test such theories, scientists run sophisticated computer simulations that model the early solar system. The results of these models consistently indicate that planetary migration is not just a possibility, but a highly likely part of our system's history. Furthermore, the concept of migration provides solutions to questions that have perplexed astronomers for decades, such as the distant placement of the gas giants. Without these movements, our solar system could look entirely different today. And as astronomers expand their search to other star systems, They are discovering that this planetary dance is a fundamental and widespread process across the cosmos. This history of planetary shifts serves as a powerful reminder that space is not a fixed backdrop, but a dynamic theater, constantly evolving with unexpected turns and transformations. Ultimately, it's truly remarkable to consider that in this immense and ancient universe, our solar system's story is defined by these grand migrations. In this cosmic play, each planet, star, and asteroid performs its part, their movements woven together in an intricate dance that persists to this very day. This phenomenon invites you to contemplate how our system's history has sculpted our present, and inspires us to keep searching for the answers that still lie hidden among the stars. So, what determines whether a planet develops moons and rings? Is their existence merely a cosmic coincidence, or does it follow a specific process rooted in the very formation of the solar system? To grasp this phenomenon, you must journey with me into a fascinating realm where gravity, matter, and chaos engage in a cosmic ballet. Planetary rings and moons are not merely celestial ornaments. They are the tangible outcomes of intricate processes playing out across the vastness of space. As planets emerged from the protoplanetary disk, they were not formed in isolation. And the constant interplay between these developing bodies within that dust and gas-filled environment frequently gave rise to these captivating satellites and structures. The genesis of planetary rings is a captivating process. Picture a disk of material orbiting a planet, much like the planets orbit the sun, composed of varying sizes of dust, ice, and rock. As these particles draw nearer to the planet, its gravitational pull becomes the determining factor. If the material ventures too close, the planet's immense gravitational force will shred it, preventing it from coalescing into a moon. However, at just the right distance, this material can gather together to create a ring. So, how do moons come into being? Moons can originate through several different mechanisms, with gravitational capture being one of the most prevalent. This happens when a celestial object, like an asteroid or comet, passes near a planet and is ensnared by its gravitational field, effectively becoming trapped in orbit. It's as if the planet extends an embrace to the passing traveler, compelling it to stay as a permanent satellite. A compelling illustration of this process is Phobos, one of Mars's moons, which is widely believed to be an asteroid captured by the red planet's gravitational pull. Sometimes, these captured objects don't just settle into orbit as moons, but are also set on a path of transformation. In the case of Phobos, it is gradually spiraling closer to Mars, and millions of years from now, may either collide with the planet or be torn apart to form a new ring. Yet, this is not the only way moons are made. Some, such as those orbiting Jupiter, showcase more complex origins. These particular moons, referred to as the Galilean moons, were formed from the very same primordial material that gave birth to the planet itself. This demonstrates that the method of lunar formation can differ dramatically, depending on the specific circumstances and history of each planet in our solar system. As planets developed over eons, some began to accumulate more material, giving rise not only to moons, but also to extensive ring systems. While Saturn is renowned as the undisputed sovereign of rings, it might surprise you to learn that other planets in our solar system also possess them, though they are far less magnificent. For instance, Jupiter, Uranus, and Neptune all have their own ring systems, which are considerably fainter and more challenging to observe. The existence of rings and moons is more than just a visually striking occurrence. It carries significant consequences for the entire solar system's ecosystem. These celestial structures can actively influence planetary dynamics and shape how planets interact with other bodies. Saturn's rings, for example, are not just for show. Their presence alters the local gravity and plays a role in stabilizing the orbits of small nearby moons. However, the story of moon and ring formation is also one of immense challenges and instability. Over time, these systems can experience profound upheavals. Collisions between moons and other objects, or gravitational disturbances from neighboring planets, can lead to the utter destruction of moons and the scattering of rings. This dynamic can create a perpetual cycle of creation and destruction, where new celestial bodies are born as others are obliterated. The history of our solar system's moons and rings is also brimming with unanswered questions, which fuels our scientific curiosity. For instance, why do certain planets host a multitude of moons, while others possess only a single one? What precise conditions allowed for the formation of colossal moons like Ganymede, the largest in the solar system, while others are so minuscule they are barely detectable? Scientists are still actively investigating the answers, continuing to delve into the intricate complexities of these celestial systems. Ultimately, while moons and rings might appear to be simple decorations in the boundless expanse of the cosmos, they serve as witnesses to a rich and complex history that stretches back to the very birth of our solar system. They recount a tale of interacting cosmic forces, the power of gravity, and the unending dance of creation and destruction across space. With each new discovery, we move a step closer to comprehending our own place in the universe and the story of our home world. So, the next time you gaze up at the night sky and see the moon shining down, I want you to remember that it is far more than a simple object. It is the product of millions of years of cosmic history, and a powerful reminder that the universe is a place filled with endless wonders and surprises. Have you ever watched a comet blaze across the heavens and asked yourself what these enigmatic objects, with their luminous tails, truly are? Both comets and asteroids can be seen as the leftover building blocks from the youth of our solar system, fragments of material that have remained largely unaltered since their creation. These bodies are not just celestial curiosities. They represent vital clues that help us understand how our cosmic home was assembled. Comets, for their part, resemble dirty snowballs made primarily of ice, dust, and rock. As they near the sun, the solar heat causes their ices to vaporize and release gas, which forms the spectacular tail that defines them. Imagine a sphere of ice melting on a hot day. What you witness is the effect of a profound transformation, a journey that unveils the object's very nature. This activity is precisely what makes comets so mesmerizing. They act as messengers from the far reaches of the solar system, carrying information about the primordial conditions that existed in our cosmic neighborhood long ago. Asteroids, by contrast, are more akin to wandering stones, the remnants of planets that never fully came to be. They are primarily concentrated in the asteroid belt, located between Mars and Jupiter, where they orbit the Sun like a vast swarm of rocks in an ocean of empty space. Some of these objects are as large as mountains, while others are no bigger than a pebble. But what makes them so significant? The answer is embedded in their history. Because asteroids are regarded as fossils of the solar system, they provide us with a direct window into the past, enabling us to better grasp how planets, and, by extension, our own world, came into existence. Have you ever wondered about the origin of these fascinating celestial objects? Both comets and asteroids were born at the same time as our solar system, assembled from the material left over from the solar nebula. Envision a massive cosmic construction site where planets are being built. In every direction, you'd find surplus materials that were never incorporated. These remnants, which never managed to coalesce into planets, are what we now know as asteroids and comets. By examining their chemical makeup, we can uncover clues about the raw materials present in that primordial nebula, which in turn reveals how the planets themselves took shape. The relationship between comets and asteroids is also quite compelling. Asteroids generally follow more predictable paths, staying within their orbits, whereas comets are far more transient, journeying across the solar system and carrying with them the basic ingredients of the nebula. This dynamic naturally makes you question the extent to which these bodies have shaped our own world. The impacts of comets and asteroids have certainly left permanent scars on Earth's history. From carving out immense craters to possibly delivering the water and organic compounds that helped life to emerge. You might think of them as a box of assorted chocolates, where you never know what the effect of each one will be until it arrives. Some were devastating, while others were constructive, supplying the very elements needed for life. One of the most captivating theories suggests that the water filling our oceans could have been delivered by comets. In a universe where life appears to be incredibly scarce, every single drop is vital. If comets were indeed responsible for bringing water to Earth, it would reframe them not as mere carriers of rock and dust, but as essential couriers of the ingredients for life itself. As we have journeyed beyond our home world, space missions have given us the chance to study these celestial bodies in unprecedented detail. For instance, the European Space Agency's Rosetta mission successfully rendezvoused with comet 67P/Churyumov-Gerasimenko, gathering invaluable data about its composition. Scientists now possess the ability to analyze the very materials these objects are made of, giving them a clearer picture of the conditions that prevailed when our solar system was forming. This exploration prompts a truly intriguing question. Could asteroids be the linchpin for humanity's future in space? Some mission concepts are already exploring the feasibility of mining resources directly from asteroids, a development that could greatly aid in the colonization of other planets. Just imagine if, in the foreseeable future, we could construct operational bases on asteroids, harnessing their materials to venture even beyond Mars. Such an achievement would not only push the boundaries of space exploration, but also redefine our entire understanding of the resources available in the cosmos. Studying comets and asteroids also forces us to consider the long-term safety of our own planet. With some asteroids following paths that could intersect with Earth's orbit, the scientific community is actively developing methods to divert these potential threats. The possibility of a major asteroid impact might sound like the plot of a science fiction film, but it's a genuine risk we must prepare for. How we choose to address this danger could very well shape the destiny of humankind. Ultimately, investigating these celestial wanderers is more than just a scientific endeavor. It serves as a powerful reminder of our deep connection to the universe. Every comet that streaks across our sky, and every asteroid that circles in the belt, is a silent observer of our solar system's long history. By grasping their origins and their influence on Earth's formation, you can gain a much deeper appreciation for our own place within this immense cosmos. In the end, comets and asteroids are far more than just inert objects adrift in the void. They represent fragments of a distant past, reminding us that everything we know, our planet included, is the product of a vast and ongoing process of creation and change. As we study and comprehend these bodies, we are not just learning about them. We are also learning about ourselves and our unique position in the vastness of space. What would you say if I told you that our planet's history has been written by a series of impacts that sculpted its surface and its narrative? You can picture Earth as an untouched canvas, where each strike from an asteroid or comet was like a new brushstroke, adding texture and color to the final portrait. But how did these collisions occur? And what was their true influence on the world we call home? When you think of Earth today, you likely picture a tranquil world rich with life. Yet, in its infancy, our planet was a realm of chaos and violence. The primordial Earth was an incredibly hostile place, subject to constant bombardment by massive celestial bodies. These impacts did more than just alter the surface. They were instrumental in forming the very atmosphere and oceans that make our world habitable. Can you even conceive of a world without water? It turns out that collisions with comets and asteroids were crucial for delivering water to our planet, transforming it into the home we recognize today. You can think of asteroids as messengers from the distant past, carrying tales from the earliest days of the solar system. As the planets were forming, these objects were the leftover debris, and a number of them took on a starring role in Earth's story, leaving behind evidence we can still study. So, what do these traces actually tell us about our past? Each impact violently carved out craters that became permanent features of our geography. But their effects ran much deeper. Some of these collisions were powerful enough to fundamentally alter Earth's chemistry. For instance, the impact of a large asteroid would have unleashed an incredible amount of energy, sufficient to ignite widespread firestorms and dramatically change the global climate. Just try to imagine how one single event could redirect the entire course of life on a planet. Scientists believe that one of the most pivotal collisions in Earth's history happened about 65 million years ago, when an asteroid the size of a mountain slammed into our planet, leading to the extinction of the dinosaurs. This single catastrophic event paved the way for the evolution of entirely new species. The lesson here is that sometimes the most profound transformations arise from the most destructive events. And it wasn't just Earth that was affected by these impacts. The Moon also bears the scars of this tumultuous period. It's a common belief that our natural satellite originated from the debris of an immense collision deep in our solar system's past. How, you might ask, could such a cataclysmic event result in the serene beauty of the Moon we gaze upon in the night sky? The narrative of our satellite serves as a powerful reminder of how creation can emerge directly from the throes of destruction. Today, the study of asteroids and comets remains an intensely captivating field for scientists. Researchers are driven to understand these celestial objects not just to unlock secrets about our origins, but also to safeguard our collective future. This raises a critical question. What would happen if an asteroid were on a direct course for Earth? The threat of such a collision is a persistent concern, making research into planetary defense more urgent than at any other time in history. Interestingly, these very collisions were instrumental in shaping the evolution of Earth's own atmosphere. As asteroids slammed into our planet's surface, they unleashed enormous quantities of gases that were fundamental to building our primordial atmosphere. It's plausible that without these ancient impacts, life as we recognize it today might never have come into being. Meaning, we owe a strange debt of gratitude to these cosmic travelers for the very air that sustains us. Beyond their physical impact, celestial collisions have profoundly influenced our culture and mythologies across civilizations. From legends of deities casting stones down from the heavens to sagas of heroes confronting celestial beasts, the notion that cosmic bodies shape earthly existence has long been embedded in our shared storytelling. How has this deep-seated narrative molded your own perception of the universe and humanity's role within it? As our exploration of space continues, we are launching an increasing number of missions to investigate asteroids and comets up close. The prospect of retrieving samples from these ancient celestial wanderers offers an unparalleled glimpse into the distant past. What incredible secrets might they hold? And how could they deepen our comprehension of Earth's formation and the development of the entire solar system? Collisions have also forged a significant legacy within the scientific community. Investigating how these powerful events altered life on our world has led to a much richer understanding of evolution and the complex dynamics of planetary systems. With every new finding, we move a step closer to solving the grand mysteries of the cosmos. Yet pressing questions remain about our own security. How can we effectively prepare for future impacts? And what technologies must we develop to deflect a threatening asteroid? The history of our planet is a wonderfully complex tapestry, woven with the dramatic threads of cosmic impacts and collisions. Each one of these formative events played a role in sculpting a world that now overflows with life. So, when you look up at the night sky, you can remember that we are all a direct consequence of this violent and creative history, living on a planet shaped by both natural forces and cosmic chaos. The late heavy bombardment theory presents one of the most compelling narratives about the solar system's tumultuous youth. Have you ever paused to consider how the Earth transformed into the planet we inhabit today? Try to picture an utterly chaotic primordial scene, bombarded by rocks and comets, where life would have struggled merely to gain a foothold, because that is the essence of what likely occurred roughly 4 billion years ago. During that era, the solar system was an entirely different and more volatile place, filled with a vast population of celestial bodies, from asteroids to comets, moving through space on unpredictable paths. The theory proposes that, over a comparatively brief span of cosmic time, a huge number of these objects rained down upon the inner planets, including our own. The reason for this celestial onslaught is found in the gravitational dynamics of the newly forming solar system, where young planets not only gathered material, but also exerted powerful gravitational forces that disturbed the orbits of countless smaller objects. Throughout the period known as the late heavy bombardment, Earth was forced to withstand an unrelenting barrage of impacts from these wandering bodies. These collisions were profoundly significant, as many scientists are convinced they were essential in creating Earth's first atmosphere. Each impact unleashed a tremendous amount of energy, sufficient to melt portions of the planet's crust and liberate the very gases that would eventually coalesce into the air. However, these impacts delivered more than just gases. A number of these asteroids and comets were rich with water and the organic compounds that are the building blocks of life. Consequently, each time one of these cosmic travelers struck the Earth, it not only carved out a crater, but also may have delivered the essential ingredients for life to begin. It's as though our young planet was receiving a steady stream of starter kits for life, containing everything necessary for the first organisms to emerge. Despite this incredibly hostile environment, Earth gradually began to find its equilibrium as the frequency of collisions decreased and the planets settled into their stable orbits. Yet there is no question that these early times were defined by overwhelming chaos and destruction. In its infancy, our world was a hot, volcanically active sphere, where any emerging life would have had virtually no chance of survival. Ultimately, the concept of the late heavy bombardment is not simply a tale of destruction. It is equally a story of creation. What might initially appear to be a sequence of ruinous impacts was, in fact, a crucial process that helped forge the Earth we know. The incredible variety of conditions that stemmed from these events enabled life to begin its journey in a setting that might otherwise have remained completely inhospitable. Scientists have uncovered a wealth of evidence that supports this compelling theory, with the craters on the moon serving as silent testimony to this ancient bombardment. By studying the lunar surface, we can read a preserved chronicle of the impacts that must have also scarred our own planet. In that context, every crater tells a piece of a story, and together, they compose a grand narrative of the solar system's chaotic youth, even though some in the scientific community still debate the theory's details. Some scientists are now proposing that the late heavy bombardment might not have been the widespread cataclysm once imagined. Is it possible that these impacts were more like a series of isolated events rather than a relentless, continuous storm of collisions? This debate is ongoing, and every fresh piece of evidence moves us a step closer to grasping the authentic history of our solar system's formative years. Science is a field in constant motion, and each new finding inevitably generates a host of new inquiries. The theory of the late heavy bombardment also compels us to consider the profound ways cosmic occurrences can shape the trajectory of life itself. Within this immense and enigmatic galaxy, the cycles of annihilation and renewal are fundamental to the process that forges new worlds, reminding us that an apparent disaster can sometimes signal the dawn of something remarkable. This era of intense bombardment left its mark, not just on our own planet, but on celestial bodies all across the solar system. Worlds such as Earth endured their own barrages of impacts, which in turn sculpted their surfaces and defined their atmospheric compositions. As a result, every planet possesses its own unique narrative, detailing the journey to its present-day state, shaped by this shared, violent past. Questions surrounding the late heavy bombardment remain a fertile ground for scientific investigation. With every new space mission launched and each astronomical observation made, researchers aim to achieve a clearer understanding of how these powerful impacts guided the evolution of the planets. This journey of discovery is truly without end, as each answer we find simply paves the way for a new set of questions. Ultimately, the theory of the late heavy bombardment does more than just illuminate the process of Earth's formation. It offers us an entirely new lens through which to view our own existence in the cosmos. It encourages you to contemplate the significant role that cosmic events play in the story of life, and to see how, even in the face of destruction, life can find a way to emerge and flourish amidst the chaos on this vast cosmic stage where we all play a part. Our planet's atmosphere is like a delicate veil enveloping the globe, and its origin is a captivating story that began in the earliest days of our solar system. But how did this gaseous shield, so essential for life, actually come to exist? To find the answer, you must journey back in time with me, to the period just after the sun ignited and the planets began to take shape. In its infancy, Earth was an utterly inhospitable realm, a searing ball of molten magma and ceaselessly erupting volcanoes. Within this extreme environment, the planet's primordial atmosphere bore no resemblance to the air we breathe today. Instead, it was composed primarily of poisonous gases like carbon dioxide and water vapor, which were continuously expelled from the planet's boiling surface. But what became of the gases that once dominated the primeval Earth? Over vast stretches of time, as the planet gradually cooled, this abundant water vapor condensed from the atmosphere and began to form the first oceans. You can picture it like a colossal pot of boiling water that, when taken off the heat, allows steam to gather and transform back into liquid, a process that was not only vital for the arrival of surface water, but also the first step toward a more stable atmosphere. Volcanic activity and the formation of these new oceans were deeply interconnected and played a crucial role in the atmosphere's development. While volcanic eruptions continued to vent gases, they also introduced new elements into the mix. For instance, nitrogen, an element absolutely essential for life as we know it, started to build up in the atmosphere during this period. Have you ever considered how we made the leap from a toxic atmosphere to one that could nurture life? The key is found in a natural phenomenon known as outgassing, where gases trapped in the Earth's interior were released, gradually establishing a new balance with the surface water and other elements. Through this process, the primordial atmosphere was slowly enriched with a new cocktail of components. Oxygen, while initially present in only trace amounts, began to make its appearance thanks to the activity of early photosynthetic microorganisms. Did you know that it was microscopic life that first initiated this worldwide transformation? As these tiny organisms steadily released oxygen as a waste product, the atmosphere started its slow journey toward becoming more hospitable for other forms of life. The accumulation of oxygen in the atmosphere brought about incredible changes. Most importantly, it enabled the formation of the ozone layer, which serves as a protective shield, absorbing the sun's most harmful ultraviolet radiation. You can think of the atmosphere as a coat that was gradually woven together from the very elements needed for life to thrive, providing a safe haven where organisms could finally develop beyond their harsh origins. However, the history of Earth's atmosphere is not simply a linear story of improvement, as it has experienced dramatic shifts over the millennia. Major events such as massive asteroid impacts, prolonged ice ages, and colossal volcanic eruptions have all significantly altered its composition. Each of these transformative occurrences left an indelible mark, shaping the destiny of both the atmosphere and the life it sustained. Have you ever paused to think about how an atmosphere can evolve throughout history? The answer is found in the continuous dialogue between living organisms and their surrounding environment. The air you breathe at this very moment is the product of a very long evolutionary journey, a mixture composed of roughly 78% nitrogen, 21% oxygen, and small amounts of other gases, a combination perfectly suited for sustaining life on our planet. This raises the critical question of what might happen if we disrupt this delicate equilibrium. Scientists are increasingly sounding the alarm about the effects of human activity on the atmosphere, from the rising concentration of greenhouse gases to widespread pollution. As our civilization progresses, we are faced with the challenge of whether we can protect this fragile, life-sustaining balance. The atmosphere is a dynamic system that constantly responds to changes. For example, an increase in atmospheric carbon dioxide is driving global warming and fundamentally altering our planet's climate patterns. This reality forces us to confront our own responsibility to safeguard this vital resource for the future. The atmosphere is not only essential for breathing, but also plays a pivotal role in regulating Earth's climate, acting as a global thermostat that maintains temperatures within a habitable range. Without this protective layer, our world would be a place of extremes, far too hot in some regions and frigidly cold in others. Have you ever considered what our world would be like without its protective atmosphere? The answer can be found by looking at the harsh environments of other celestial bodies that lack this vital shield. Our atmosphere is also fundamental to communication and navigation, as everything from the sound traveling on the wind to the radio signals connecting us globally relies on this gaseous envelope. Without it, the way we live would be unrecognizably different. The atmosphere is far more than just a physical layer. It serves as an essential medium that unites all forms of life on the planet. When you reflect on this, it becomes evident that the formation and development of Earth's atmosphere is an incredibly intricate and captivating story. It has shifted and transformed over eons, reacting to the emergence of life and profound environmental changes, making its history one of constant adaptation. Understanding the origins of our atmosphere allows us to truly grasp the delicacy of this system and recognize why its protection is so critical. So, the next time you pause to take a deep breath, consider the immense history contained within that single act. Every inhalation you take is a direct connection to millions of years of planetary evolution and transformation, a reminder that you are carrying a piece of Earth's story with you. The creation of other solar systems is a compelling subject that encourages us to explore the sheer variety of the cosmos. Have you ever asked yourself if our own solar system is a cosmic rarity, or if similar systems are common? The truth is, our galaxy is home to countless solar systems, each with a unique origin story much like our own. In the immense expanse of space, as stars are born and eventually die, they foster the diverse conditions necessary for new planetary systems to arise. These systems are like cosmic experiments, where the specific ingredients and local conditions dictate the final outcome. While some may share characteristics with our own, many others are profoundly different, filled with unexpected wonders. The diversity in how solar systems form is influenced by several key factors, with the type of nebula from which they originate being one of the most significant. Some nebulae are dense with materials, perfect for forming systems with numerous planets, whereas others with fewer elements may give rise to simpler planetary arrangements. Modern technological breakthroughs have empowered astronomers to observe and analyze these systems during their formation. Imagine a telescope with the power to peer thousands of light years into space. Using such instruments, scientists have identified protoplanetary disks swirling around young stars, which confirms that the process of creating planets is actively happening in other regions of the universe. Some of these disks are so unlike our own system that they challenge us to imagine what life could look like on such worlds. For instance, some solar systems feature planets that orbit incredibly close to their star, resulting in scorching surface temperatures, while others possess gas giants positioned much farther out. What does this variation mean for the possibility of life? Each of these systems offers a distinct set of conditions that may or may not support life as we understand it. The arrangement of planets also differs greatly. In some systems, they are tightly clustered, while in others they are widely dispersed, prompting questions about the gravitational forces and interactions that shape their distribution. Remarkably, some of the solar systems we can observe are in their earliest formative stages, still in the process of building their planets and moons. To witness these systems in their infancy is like watching a child grow, brimming with potential and countless possibilities. It leads us to wonder what they will become over cosmic timescales, and if we will one day find worlds similar to our own among them. This comparison also raises profound questions about the long-term fate of celestial bodies, and whether their futures will diverge dramatically from our own. The ongoing search for exoplanets has launched a new era in our comprehension of solar system formation. With each new discovery, we are confronted with more questions, yet every answer brings us a step closer to understanding our own place in the cosmos. Scientists are particularly interested in planets located within the habitable zones of their stars, where conditions could permit liquid water to exist. This sparks the tantalizing question of whether we are truly alone, or if other beings are out there, gazing up at their own stars. The incredible variety of planets, their orbital paths, and their physical properties reveal that nature is endlessly creative in its experimentation with the universe's building blocks. Investigating these distant systems is more than a scientific objective. It's a profound quest to find our own position within the vast tapestry of existence. The story of their formation is a powerful reminder that the universe is a dynamic, ever-evolving place, and human curiosity is the engine that drives us to keep exploring its mysteries. This particular question is absolutely central to grasping how our solar system came into being. Since the dawn of civilization, people like you have gazed at the heavens, searching for clues about our cosmic origins. The answer, it turns out, lies with nebulae, vast, drifting clouds of gas and dust that serve as the very key to understanding the birth of both stars and planetary systems. So, how can you be certain that the solar nebula theory is the correct explanation? A primary line of evidence emerges from observing other nebulae scattered throughout the cosmos. Through the use of powerful telescopes, astronomers can now scrutinize these magnificent structures, which you can think of as cosmic nurseries, where new stars are taking shape right now. By watching these distant nebulae, scientists have witnessed the development of protoplanetary disks, which is precisely how our own solar system is believed to have formed, giving us a unique window into our own distant past. Another compelling piece of evidence lies in the chemical makeup of the Sun and its planets. The majority of elements you find right here on Earth, including carbon, oxygen, and hydrogen, are also abundant in nebulae, which strongly implies that we are forged from the same stellar material. Beyond basic elements, scientists have examined isotopes, variants of an element with different numbers of neutrons, and found that the isotopic ratios in meteorites are remarkably similar to those in the Sun. This discovery provides a crucial link, suggesting the material in these meteorites is a pristine remnant from that primordial cloud. Further support for this idea comes from sophisticated computer simulations. Scientists have developed models that successfully replicate the formation of a solar system from a collapsing nebula, showing how gravity can forge a protoplanetary disk where material clumps together to become planets. When you compare the outcomes of these virtual models with actual observations of the universe, the consistency is truly striking. This is reinforced by observations of other solar systems, where astronomers have directly detected the same kinds of dust and gas disks around young stars, confirming the predictions of the solar nebula theory. Even the smaller bodies in our cosmic neighborhood, like comets and asteroids, contribute to this narrative. These objects are essentially fossils from the solar system's formative period, and by analyzing their composition, scientists confirm they are made of the exact materials you would expect to find in a nebula. Looking even further afield, the discovery of exoplanets, worlds orbiting other stars, has been revolutionary. Observing these planets as they form within protoplanetary disks gives us insight into the diverse ways planetary systems can be created. Ultimately, the evidence for the solar nebula theory is so strong because it aligns with a broad scientific consensus on how stars themselves are born. The processes that created our sun are not an isolated occurrence, but a universal phenomenon happening across the galaxy. Yet, this doesn't mean we have all the answers. Crucial questions remain, such as what initially triggers a nebula's collapse, or why some form planets while others don't. These persistent mysteries are what continue to propel scientific research forward. As technology advances, our capacity to investigate these questions grows more powerful. Every new image from a space telescope and each analysis of a meteorite brings you closer to a complete picture of our cosmic history. It's vital to remember that science is an ever-evolving process. What we hold as true today may be refined by future discoveries. The solar nebula theory, while robust, is a living idea that will continue to be tested and improved upon as our search for origins continues. So, as you look to the future, remember that countless new stars and planets are being born across the universe, each with a unique story waiting to be told. The formation of our solar system is an enthralling subject, but it's one that still holds many challenges and unresolved puzzles. The history of our cosmic home is a grand narrative filled with unexpected turns, and it's a story that is still very much being written. One of the most fundamental questions you might ask is why we even need a theory about the formation of the solar system. The answer is that such a theory not only illuminates the origin of our own cosmic home, but also provides a framework for understanding how other planetary systems throughout the galaxy may have come into existence. However, The constant influx of new astronomical data and unexpected discoveries can transform a seemingly straightforward picture into something far more intricate. As fresh evidence comes to light, established theories can be challenged and even fundamentally rewritten. The history of the solar nebula theory itself is a compelling example of this scientific process. While this theory enjoys widespread support among scientists, some researchers propose that alternative models could provide a better explanation for our observations. For instance, the idea that our solar system originated from a single nebula has been contested by models suggesting multiple nebulae or the critical influence of nearby stars. This raises the fascinating possibility that our system's creation might be the result of a combination of these different scenarios. Even proponents of the solar nebula theory acknowledge that certain details don't align perfectly with its predictions. The distribution and orbits of the planets, for example, do not entirely match what you would expect from a uniform formation process. This discrepancy has led to the compelling hypothesis that the planets may have migrated to their current locations long after they first formed, a topic that ignites passionate debate within the astrophysics community. Another point of discussion revolves around the role of dwarf planets like Pluto. These small celestial bodies compel us to consider whether the solar nebula theory can be adapted to account for smaller objects that don't neatly fit the conventional narrative. Are they an integral part of our system's formative history, or should we view them as mere cosmic eccentricities? The gas giants, Jupiter and Saturn, also introduce their own set of complex questions. They are believed to have played a pivotal role in the solar system's development, but the specifics of their influence on the formation of terrestrial planets remain unclear. The immense gravity of these giants could have either gathered or scattered material within the early protoplanetary disk, profoundly affecting how smaller worlds like Earth took shape, making you wonder if their presence was ultimately a benefit or a detriment to us. Furthermore, the discovery of exoplanets has vastly expanded our understanding of what is possible. We have identified solar systems with structures that bear no resemblance to our own, challenging the notion that planetary formation follows a universal template. This forces you to ask, are we witnessing just a small fraction of a much larger and more varied cosmic puzzle? It may be that new theories are necessary to integrate these diverse discoveries and create a more comprehensive understanding of the sheer variety of solar systems in the universe. Planetary migration, which I mentioned earlier, is another phenomenon that fuels intense scientific discussion. The concept that planets can shift from their original orbits can drastically alter a system's dynamics, making you rethink the stability of our own cosmic home, and consider if Earth's current position is the result of an ancient, unexpected journey through space. As our technology advances and our observational instruments become more powerful, new and more profound questions emerge. We are now investigating how nebulae themselves actually form, and what fundamental physical processes are at play that we have yet to comprehend. These inquiries drive our continuous exploration and our search for answers that could reshape our entire understanding of the cosmos. We also cannot overlook the significant impact of collisions on Earth's history. While we are certain these events molded our planet, their precise role in creating the conditions necessary for life itself is a frontier of research yet to be fully explored. This field connects the grand story of the solar system's formation directly to the mystery of our own existence. The search for answers is an ongoing endeavor. As we learn more about our solar system, we naturally look outward to other systems with even greater curiosity. Could we one day find life elsewhere? And how would our formation theories compare and contrast across different cosmic settings? These questions keep us in a perpetual state of wonder and drive our scientific pursuits. Ultimately, It is vital to remember that science is a continuously evolving process, not a static set of facts. The theories we embrace today may be substantially revised, or even entirely replaced by the discoveries of tomorrow. It is this inherent dynamism and capacity for change that makes the scientific endeavor so incredibly exciting. Therefore, maintaining an openness to new ideas and innovative approaches is fundamental to comprehending the full complexity of the universe we inhabit. The current debates and challenges surrounding the theory of solar system formation represent just the beginning of a journey we are only now undertaking. As we persist in exploring, investigating, and questioning, the mystery of our place in the cosmos will gradually unravel, revealing a history far richer and more complex than we could ever have imagined. Human curiosity is truly boundless, and our quest to understand the universe has no conceivable end. Have you ever looked up at the star-filled sky and wondered how everything you see came to be? The history of our solar system reads like an epic tale, filled with captivating events and profound mysteries that remain to be solved. As we approach the end of this journey through the birth of our solar system, it is important to reflect on what we have learned and the deeper significance of this knowledge in our lives. From the sun's initial spark to the assembly of our planets, every step in this cosmic process was absolutely crucial. But why is it so important for you to understand how our cosmic home was built? Knowing our celestial history not only helps us comprehend our own place in the universe, but also gives us clues about how other solar systems might evolve across the vastness of space. It is like being handed a map that can guide you through the intricate labyrinth of stars and planets. The solar nebula theory, with its compelling story of collapsing clouds of gas and dust, provides us with a window into this distant past. This theory illustrates how initial chaos eventually gave rise to the elegant order of our solar system. This knowledge is not merely academic. It empowers you to draw direct connections between events occurring in the cosmos and our own experiences here on Earth. So, what role do the planets themselves play in this extraordinary story? When you explore how planets come into being, you gain a deeper appreciation for the distinctions between the worlds around us. You have the terrestrial planets, defined by their solid ground and distinct personalities, standing in stark contrast to the immense and enigmatic gas giants. This sheer variety reveals the countless ways that matter can arrange itself across the vastness of time and space. The force of gravity is another crucial element in this cosmic story. It is the power that pulls celestial bodies together, causing them to form and engage in an intricate dance that feels almost orchestrated. Your solar system simply wouldn't exist as it does without this fundamental force. But gravity's influence extends to you on Earth as well, not only by holding our world in its orbit, but by maintaining the delicate equilibrium that allows for everything you know. Speaking of equilibrium, the concept of planetary migration introduces a fascinating layer of complexity. This is the process by which planets shift their orbital paths over immense timescales, challenging our notions of a static solar system. You have to wonder what might occur if Earth were to drift closer to the Sun, or what consequences would unfold if it moved farther out. Such questions force you to contemplate the fragile stability of our own environment, where even slight adjustments can lead to profound changes. Your understanding is further enriched when you observe the moons and rings that populate our system. Each moon is essentially a miniature world in its own right, a constant companion to its much larger parent planet, while the rings around the gas giants are like brilliant, shimmering halos. What enigmas might these moons conceal? Investigating them could unlock secrets about their own formation and provide valuable insights into the histories of the planets they orbit. Comets and asteroids, the wandering travelers of ice and rock that traverse our solar system, represent critical pieces of this grand puzzle. These objects give you a direct look at the primordial building blocks that formed our world. You are left to consider if they might have carried the very components that enabled life to emerge on Earth, a thought that makes you reflect on both your own origins and those of other planets. One of the most dramatic chapters in this narrative is the Late Heavy Bombardment, a chaotic period of massive impacts that sculpted the surfaces of the inner planets. This violent era serves as a powerful reminder that the universe is a constantly changing and at times unforgiving place. How did this relentless bombardment affect the development of our atmosphere and the rise of life? The clues likely reside within the ancient rocks of our planet and the scarred surface of the moon. The development of Earth's atmosphere is yet another captivating tale of transformation. It evolved from a completely inhospitable environment into the very sanctuary that sustains you today, a transition marked by profound chemical and physical changes. Pinpointing the factors behind this shift helps you to grasp the delicate nature of our current climate and underscores the critical need to preserve it. As you begin to survey other solar systems throughout our galaxy, it becomes clear that this cosmic saga extends far beyond our own neighborhood. Each star you see in the night sky could be host to its own planetary system, perhaps with worlds resembling ours. The possibility of other habitable planets fuels an ongoing search, and every new finding brings you a step closer to grasping your true position in the cosmos. The solar nebula theory, which describes the formation of our system from a swirling cloud of gas and dust, is supported by a growing mountain of evidence. With every technological leap and new observation, scientists are peeling back more layers of our cosmic origins. Even so, a great number of questions persist, and you can only imagine what incredible mysteries are still waiting to be discovered in the depths of space. When you consider the modern scientific landscape, it's obvious that the quest for knowledge is a perpetual motion machine. Every discovery, rather than being an endpoint, serves as a catalyst for entirely new lines of inquiry. This insatiable curiosity is the engine that propels humanity forward, driving us toward ever greater exploration and understanding. Ultimately, the story of our solar system is an epic journey that you are only in the initial stages of comprehending. As you persist in asking questions and exploring the unknown, you not only solve the riddles of the universe, but also find answers about your own existence. It is this profound curiosity that pushes us to look deeper, and perhaps one day you will not only understand the genesis of our cosmic home, but also glimpse the destiny that awaits us in the great expanse.